Okay, we won't go into what they exist for. Okay, we will talk about what they are. All right. Okay, so today we're going to learn the sum and difference formulas. Okay, and we'll also too cover what's called the double angle formula as well, because the double angle formula are actually just a special consequence of the sum and difference formulas. Okay. They are on the sheet. Okay. Why do we have a sum and difference formula? As we saw detailing in the class yesterday, we didn't get quite through it all. Sometimes you might be asked to calculate by hand something like the sine of 75 degrees, or 75 degrees. Okay. And if I'm calculating this by hand, I actually can't do it. Okay? The reason why is simply because I don't know from my unit circle what the sine of 75 is. It's not one of the special locations. Okay? The special locations are 30 degrees, 45 degrees, and 60 degrees. Okay? I can also, or in radians, pi over 6, pi over 4, and pi over 3. Okay? So, this, it would seem like we can't handle this, right? The thing though is, if you can, look for opportunities to rewrite the angle. In this case, I happen to know 75 degrees is 45 degrees plus 30 degrees, correct? Okay. So I could go ahead and rewrite things that way. Okay. I can make this the sine of 30 degrees plus 45 degrees. Okay. Now, this isn't the sine of 30 degrees plus the sine of 45 degrees. This is the sine of 30 degrees plus 45 degrees. So there's a big difference there. That's still 75 degrees in there. Okay? The difference, though, is I can now actually handle this because I know what the sine of 30 degrees is. I know what the sine of 45 degrees is. I can use one of these sum and difference formula to work this thing out. In fact, the sum and difference formula that would work on this one would make this out to be the sine of 30 times cosine of 45 plus cosine of 30 sine of 45, okay? And each of these individual pieces I know the answer to. What's the sine of 30 degrees equal to? A half, right? This would be 1/2. Cosine of 45 degrees would be root 2 over 2, right? Cosine of 30 degrees would be root 3 over 2. Sine 45 would be root 2 over 2. We multiply these together, that gives me 4, or root 2 over 4, plus root 6 over 4. Okay? And I can combine those two just to become root 2 plus root 6 all over 4. And that's as far as I can go. Okay? But there we had it. We could work this out into an actual answer, to get a numerical answer.
So you just look for radians? Really?
Huh?
You just look for the...
Yeah, you just look on the unit circle, yeah, where they come out to be. So we did this in degrees. I could do this in radians as well. It works the same way, okay? But the sine of 75 degrees is this number right here. Not a nice number, is it? No, but it's an actual number, right? We were able to figure that out without the use of the calculator and get our answer, okay? That's what the sum and difference formulas are for. They allow us to do this sort of solution, okay? Now, the actual formulas, I'm going to go ahead and take a moment to write them out, let you guys copy this down. And we'll look at the formulas, because there's formulas for the sine, the cosine, and the tangent, okay? Depending on how we do. And you'll also see why we call them sum and difference. Because guess what? I could do the same thing with a minus. If I asked you to figure out what the sine of 15 degrees was, okay? 15 degrees, again, is not on the unit circle, but I can figure it out by doing 45 degrees minus 30 degrees, right? And so be able to write that out that way. We'll look at that in a second, okay? This is what we get here. Any questions so far? All right. Huh?
Root 2 over 4 plus 6 over 4.
Yeah, so it's root 2 over 4 plus root 6 over 4, which is root 2 plus root 6 all over 4, okay? All right. So the actual formula are for the sine, the way we typically write these, by the way, the sheet I think has it sine of u plus sine of v. You can see it that way. You'll typically see a and b, things like that. They're just angles. They're placeholders. You can use x and y if you want to. Okay, it's just again a placeholder. I'm going to use A and B. Okay, where A is an angle and B is an angle. Okay, we have the sine of A plus or minus B. Okay, when you see plus or minus, that's just telling you where one version is plus, one version is minus. Okay, so when it's sine of A plus B, you get this. When it's sine of A minus B, you get this. And it comes out to be the sine of A times the cosine of B plus or minus the sine of B cosine of A. Okay? And again, these things are commutative. So if you wrote those like cosine of A, sine of B, plus sine of A, cosine of B, that'd still be correct. Things like that. You could write them, you could, it's the only thing is that you have a sine and cosine, the angles are different here. Whoops. And then, oh, come on, don't do that. Go back, undo, 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 undo. There we go. Okay, the only difference is that whatever they are over here, they're flipped over there. Okay, the angles. All right, and then the sign just follows whatever the sign was. So if it's A plus B, it's plus in this. If it's minus in the formula. Okay. Other than that, it's just a matter of plugging in things in the formula. Okay. It's not a particularly hard formula to memorize. There's not much going on there. Okay.
How does this work? Or like, how is it derived? Why is
The derivation of it takes a lot longer than we have class time
okay,
for.
cool, okay. Okay, nothing we should
We could do it. It just would take
Yeah.
us too much time. In fact,
of course. Okay.
there's a book over there called I think it's like Heavenly Mathematics or something like that. That talks about how the first chapter talks about how you would get this formula, and then like how you would use it. And because one of the big things for it is, notice how in a calculator I can earn sine of like 5 degrees, it gives me an answer, or sine of 6 degrees, it gives me an answer. You use this formula to find all that out. Okay. Because once you get what one thing is, like what the sine of 15 degrees is, you can use that to find a bunch of other formulas and things. Okay. So.
yeah, that's true.
Kind of like that. So that's how this thing is used, okay? And so somebody actually sat down and did that for every single degree up to a certain point, okay? And that's what they got programmed in your calculator. So, this is the one for the sine. Cosine, the formula for the cosine is very similar. So it's cosine of A plus or minus B, okay? The big difference here, though, is that we don't flip-flop angles, we flip-flop what they are, things. So it's the sine of A, sine of B, and here's where it gets really tricky. It's minus plus cosine of A, cosine of B. So the sign flips, okay? So if it's cosine of A plus B, it's a minus sign over here. If it's cosine of A minus B, it's a plus sign over there, okay? Everyone catch that?
What?
The sign here
It's always opposite.
is opposite. Okay, so if it's plus over here, it's minus in the formula. If it's minus over here, it's plus in the formula. Okay? But look how similar it is to the sign. It's very similar, right? Okay, and again, you just have the two pieces together like so. Okay? Any questions there? All right. The last one is the one for the tangent. Okay? The tangent of A plus B. Okay? The tangent one is the one that's going to be kind of much more different than these. It's the outlier. The tangent would be the tangent of A plus or minus the tangent of B all over 1 minus plus the tangent of A times tangent of B.
That's not holding.
Yes, that one is
Wait,
much
one.
nastier. Okay.
Minus
Yep.
Okay.
So again, there's two sides in there and they flip, and there's, tangent ends up being a lot more difficult. Okay. But again, all these things are just a matter of plugging in numbers to getting this thing work. Okay. So for example, okay, if I asked you to do the cosine of pi over 4 plus, or pi over 3 plus pi over 4, okay? So this would be 60 plus 45, so 105-degree angle. One that's not one we know, okay? If I asked you to do this one, you could, okay? Because you would just apply this formula to it. I would come through and I'd say, okay, the sine of pi over 3 times the sine of pi over 4 minus the cosine of pi over 3 cosine of pi over 4. And then each of those are things I know from the unit circle. I can just replace and go. Right? Okay? So that's the sort of idea you have here. Okay? That's what this is primarily used for. Any questions? It's very much more than joke. Okay?
Oh, that would be nice.
And these are used, remember too, by the way, these are two-way streets. Okay? So if I've got something like this, I can reverse it back to this over here. Okay? And sometimes that's useful to do. Okay? So besides solving to figure out what angles are that you don't have, these are another set of identities you can use in a problem to simplify things out or make the substitutions. Okay? You'll see those particularly happen when you get like certain ones. Like there's an exercise in the homework for this that I'm going to put on there, which is derive the formula for the sine of 3x. Okay? Which you're going to see how to do in a minute. Okay? But it can be done based off of these right here. Okay? Everyone got that? Alright. So, these are those sum and difference formulas and how they're used. They're fairly straightforward. Now, there's another set of formulas based off of these called the double angle formulas. Okay? What the double angle formulae do is they handle things with the angles being doubled. So for example, if I came up here and wrote, solve the sine of 2x equals 1, okay? I could go through here and do like arc sine on both sides and things like that. But to know that I can handle this is to figure out what the sine of 2x is. Rewrite the sine of 2x somehow. Anyone have any idea of how I would do that? How else can I write 2x?
Foil.
I can write it as,
Sine, you write as 2 sine over 4 sine.
okay, that's the formula, but why is that the formula? How else can I write sine of 2x?
Sine 2 times sine.
I can write, no, not sine 2, sine x. But how about the sine of x plus x, right? What's x plus x? 2x. So I can come through here and rewrite this actually, okay, as the sine of x plus x. And now if I apply the sum and difference formula to this, what do I get? I would have the sine of x cosine of x plus sine of x cosine of x. Okay? You could say, oh, I'm flip-flopping, but it's the same letter, so it comes out the same way for both, right? Which comes out to be, as you said, Jackson, 2 sine of x cosine of x. Okay?
What happened to the 1?
I haven't put the equals 1 yet. The equals 1, that's just an example, okay? The actual formula is what I just wrote out, okay?
That's one of the double angles.
That's a double angle formula. That's the double angle formula for the sine, okay? And so, the actual double angle formulas, all of them can be derived, just like I did right here. But the one for the sine, so the sine of 2a would be 2 sine of a cosine of a. The cosine one has several different ways you can write it, okay? The primary way you can write it, though, okay, is the cosine squared minus the sine squared, okay? Crap. It's a bit stupid. It's okay. I'll go back and fix it here in a second. So I can write this as cosine squared of a minus sine squared of a. But that looks suspiciously a lot like a Pythagorean theorem, doesn't it?
So let's say 2 sine A cosine A.
Yeah. 2 sine a cosine
This is
a.
the same
Okay.
problem.
And in fact, I could do so. I could rewrite that cosine squared as 1 minus the sine squared to make this 1 minus 2 sine squared of A. And I can also replace the sine squared with 1 minus the cosine. Okay, but there's a minus sign out front, so it becomes positive cosine, so it becomes 2 cosine of A, cosine squared of A minus 1. Okay, so these are all different ways I can write the cosine. Okay, everyone got that?
So on the test, you're gonna ask us to derive these identities from other identities?
I might ask you to give me the double angle formulas
Yeah.
from the sum difference formula, or just show why that would be the case. That is a reasonable question, because it's not that hard to do.
Yeah.
The double angles are just applications of the single angle. So, okay.
On the last one, how do you make cosine squared into what? Do you divide by?
Oh, so like right here, how do I get these two?
Yeah.
Okay. I'm going to replace that with its Pythagorean identity,
Which is.
which would be 1 minus sine squared.
Yeah.
Okay, which is how I get this right here. And then for the second one, I do the same thing but replace the sine. Okay. Now, before I do the tangent of 2a, Mr. Dow goofed. This actually is flipped around. It does kind of make a bit of a difference. No, not the whole thing. Just this. No. Just this part. Okay. There you go. Okay. So make sure you correct that in your notes. I flipped them by accident. Okay. Right now. Okay.
So cosine.
Cosine comes first, and the cosine comes. Yes, sine comes second. All right. This is what they come out to down here. Any questions there? Nope. All right. The last one would be the one for the tangent. And its formula, remember, was tangent of A plus tangent of B. So this would be tangent of A, tangent of A. So it would be 2 tangent of A on top. And on bottom, it would be 1 minus the tangent of A, or tangent squared of A. Okay, so the formula comes out. And again, that was easily derived from the tangent double angle formula. Okay? Any questions there?
Why does the tangent one always look so bad?
Oh, it's part of the reason is because remember tangent sine over cosine. So think of it this way: to get that tangent formula, I'm actually doing the sine one over the cosine one, and then cleaning it up to get it all back in terms of tangents. Okay, yeah. It's also why notice what's suspiciously absent here. No, not for this. But we did sine, cosine, and tangent. What about the others?
They're way harder.
Actually, they're not. If I wanted, like, well, no, not really. What's the cosecant in relation to the sine? 1 over. So what do you think I have to do here? 1 over. So I wanted the cosecant formula.
Oh, because the formulas to get them the same.
Exactly.
Same ratio.
Yep. So if I wanted the cosecant one, so the cosecant of 2a is literally 1 over 2 sine of a cosine of a. Okay? That's why we don't bother with those, because they're literally just 1 over what we got.
Identities on identities.
Yep. Identities on identities. Yeah.
A and the denominator?
Yes. Yeah. It's all the same letter throughout. Okay. Okay. Sorry about my terrible handwriting. Alright.
Sorry.
Yeah.
Why would be 1 minus tangent?
Tangent squared?
Yeah.
Remember, it's based off of this formula right here. Okay. This formula right here. Okay. My shoes are actually like literally the same.
Yeah.
I think you just have like a slightly different color version of the shoes I'm wearing. That's crazy. Alright.
You guys match the
Well, if I look at this tangent one here, tangent of A plus tangent of B, it's plus right here. Remember, it's 2A, so it'd be tangent of A plus tangent of A. On the bottom, it's 1 minus tangent of A times tangent of A, which is how we
Yeah,
get.
it has to be. Oh.
Come on, smart boy. Don't do this to me. There you go. Okay? Those are the double angle formulas. And again, you would use them. You use them for the primary uses of these guys. One use is to solve for angles you can't normally solve for. Okay, so try to think of an example. So I gave that example before. One of the exercises for homework was figuring out what the sine of 3a is. Okay, how I would do that is rewrite that as the sine of 2a plus a. And the 2a part is the double angle formula, okay? But then the sine but then you add it to the regular sum and difference formula. And you can work it out that way, okay? So you would end up having like, yeah, you have things come out nicely that way, okay? So it gets kind of long because there's a lot going through, but it's easy to do actually, just follow the rules, okay? So that's one example. But yeah, so if I have angles, I can figure out other angles from them, okay? So we figured out the angle at the very beginning of class. We figured out what the sine of 75 was. If I wanted to find the sine of 150, now that I know what the sine of 75 is, I can apply that here and get the sine of 150. Okay? So if I did that, the sine of 150 would be equal to the sine of 2 times 75, which is equal to 2 sine 75 cosine 75. We actually don't know what the cosine 75 is, but we can figure it out by hand using the same way we figured out the sine of 75. And so from a previous problem, we figured out what the sine of 75 was, so I can just substitute that in. I can quickly, easily figure out what the cosine of 75 was, substitute that in, get an answer, so I'm able by hand to figure out what the sine of 150 is without having, by just using these formulas. And that's what they're really for. And again, that's what people did back in the day, when you had to figure out, or rather, somebody went through, well, the book is being used probably for the camera. Like literally, in times before calculators, someone honestly went through and did this, and just created a big table, and every time they got a new angle, they wrote it down, and then went through and were able to get every single angle there is through this method. Okay, from 0 to 360.
Of like the girl who wrote the code for the launch that led down the road, and she was like leaning against the stack of code as hard as she was all by hand.
Yep. Yeah, back in the day, we take computers for granted, but I mean there was a lot of work that went into it. They've also gotten a lot smaller too. In the olden times, like computers,
Years ago, they take up an entire room.
yeah, they could take up an entire room or entire floor of a building, depending on how much computing power you need. Now, my dumb phone here has the, okay, my little dumb phone here has just as much computing power as those did. In fact, this has more computing power than the Apollo one is.
Yeah.
Okay. I would imagine, I could not imagine what NASA would do if they had something like this, which is essentially a handheld computer of, that is just so much faster and better than what they had.
That's sci-fi.
It's crazy.
They had our iPhones back then.
Yeah, they could have really, iPhones had more. What's really crazy though, is once the hardware is built, it's really hard to change things. So there are still NASA systems that were built back in the 80s that have to use old school software and old school, things because making.
You have to place entire infrastructure.
Yes, you'd have to place all the infrastructure. So, like for example, I was reading an article. The International Space Station, its telemetry computer, the thing that controls where it goes, runs off of MS-DOS 7, which is the precursor to Windows. Okay, because the hardware was built at a time when that was what you used. Okay, now you can think of this as one of two ways. That's really primitive, or it also tells you though that you don't really need all that much computing power to have a spaceship fly correctly. Okay, because all it really needs to do is be able to say where you're going. It doesn't need to do all this fancy stuff. Okay. But yeah, or there's other things too, like NASA is the largest purchaser of floppy disks in the world right now. So floppy disk was how you would save stuff before like thumb drives and things like that. Now the floppy disks they're buying, they're not the little 3.5s. Okay, they're not the 5 1/4 ones. They're the giant 7 and like 3/8 ones. They're like this big.
Can't imagine how many providers for this.
Nope, there aren't. And so apparently people have put people clearing out like old storage warehouses and things like that would find a bunch of those, put them up on eBay, and have them bought. And it turns out it was NASA buying them. So there's somebody at NASA whose job is to buy giant floppy disks to search the internet. Yeah, so they can because they need them for what they do. Okay, and upgrading that system would, they'd have to basically shut everything down for a certain period of time to update it. They just can't do that, especially with you have actual people missions ongoing.
So are we gonna go dark for about half a year?
Yeah. Good luck, space station, or good luck, space probes. Hopefully you don't run into anything.
Have you seen that commercial for like Rosetta Stone or something? It's like the German Coast Guard guy, and he gets a radio call. It's like, Mayday, we're sinking. And he's like, what are you sinking about?
I've not seen that, but I like the ones where they used to have the print advertisement for Rosetta Stone that you'd see in magazines. This was like a while back, which was she was an Italian supermodel. He was a simple farm boy from Kansas. He had only one opportunity to impress her. It was like Rosetta Stone. You see him holding a copy of Rosetta Stone behind
That
him.
boy's coming back from the field or what?
Yeah.
I can just imagine that meeting. They're like, wow, you almost kind of speak Italian. See ya.
Well, it's impressive is how well that program actually works. And it's what the government uses. A lot of governments and companies use it to just get people up to speed. So
The Mormons have a very efficient language school
as well
for their missionaries.
know that.
It's on par apparently with the DLI in Monterey, California. Defense Language Institute is going to send all the people up for languages.
When they have to do so. When they have more time than they need, and when they have enough time to learn the language, but not enough time to, immerse themselves. That's what they get set up.
The immersion comes after.
When they're in a pinch, they're just using this.
If you want to make money in the military, go to nuclear for the Navy. They'll pay $100,000 yearly in bonuses. They'll pay for your schooling, or in the Army, or in Arabic or Chinese, because they don't have enough translators, so they'll pay a lot.
There you go. Career path for anybody in here. Learn some Chinese. All right. Any questions on how these things work? Let's take a look at a few examples. Okay. Hold them out because coming up with good examples off the top of my head with these things is tougher mainly because I want to write them correctly for you. So you might have something like excuse me. You might be told, find the exact value of the following. So you might have something like the sine of 2 pi over 3 plus 5 pi over 6. Okay? Way to do that is just, again, use sum of difference formula. So what would the formula for this one give me? It would be what? Sine of
2 pi over 3.
2 pi over 3.
Cosine 5 over 6.
Cosine 5 pi over 6. Okay, then what?
Plus, right?
Plus
Sine 5 over 6.
sine of 5 pi over 6.
And 2 pi
Cosine 2 pi over 3. And then this just becomes a matter of figuring out what each of those things are. Sine of 2 pi over 3 should be root 3 over 3. Root 3 over 2. Yes. Cosine of 5 pi over 6 should be minus root 3 over 2. Okay, plus the sine of 5 pi over 6 is 1/2, right? And the cosine of 2 pi over 3 should be minus 1/2. Okay? Again, unit circle, guys. Make sure you got that down. You should be able to round those things off. No, I put my minus sign in there. It's still in the correct shape. Okay? So, at this point, working this out here, the top here is going to give me what? Root 3 times negative root 3 is negative 3/4 plus negative 1/4 is equal to negative 4/4 or negative 1. Okay? Now, well, negative 1, this is the sign of negative 1. Isn't that happen at 3 pi over 2? Yeah, doesn't it? Well, add these guys together. We have 4 pi over 6 plus 5 pi over 6. That's 9 pi over 6, which factor the 3's out is 3 pi over 2. So sometimes you don't actually have to use the formulas. Okay? Sometimes if you add the two angles together, it might equal something you already know. In which case, do it that way, because that's way easier. Okay? But that's basically what you do with these things. Now, the other thing you could do with these things is use them to solve trigonometric equations. Let me give you an example of that. Okay? Suppose I had, the sine of x plus pi over 3 is equal to 1. And I want to solve this out. Okay? Now, I happen to already know the solution to it. Okay? Because I can just think, well, what do you add to pi over 3 to get it to be pi over 2? Okay? That's one way you could approach this. But let's say you didn't know that. Well, you could do the sum and difference formula here. We could rewrite this out as the sine of x cosine of pi over 3 plus the sine of pi over 3 cosine of x all equal to 1. Okay? Well, each of these things, we know what the cosine of pi over 3 is and the sine of pi over 3 is. So I can make those replacements. This will be 1/2 sine of x plus, okay, root 3 over 2 cosine of x, okay, is equal to 1, okay? And then from there, we could just do some more cleanup. So I might move the sine of x over, I might do something else, but you would just start working away at this thing until you get it to something you solve. And remember, if you get stuck, like let's say I can't figure out the exact answer here, I can't get it to a point where I can say, oh, sine or tangent or whatever is equal to this clearly, let's go. Okay? The other way to handle this is to do what at this point? Make everything sine. Yeah, it's a little hard to do with the cosine. But what else could I do? Graphing calculator. Okay? I can use the graphing calculator and have it work out that way. Okay? Any questions there? By the way, anybody figure out what the answer is? I know the answer without even doing the graphing calculator. What do I add to pi over 3 to get it to equal to 1? Or to get it equal to pi over 2? Nope. Pi over 6.
Pi over 6.
Okay. Pi over 6.
So wait, if you did this algebraically, would you divide by sine or would you divide by...
At this point here, it gets a little trickier to handle.
Yeah.
Right here, because the sine and the cosines kind of get in your way.
So graph this.
I would graph this if I really needed to figure it out. Or do what I did in the beginning. Just figure out, look at the unit circle and figure out what that is. Another thing I could do is I could try to get one of the terms by themselves and then kind of clean things up that way. Okay? And get this into be a fraction or something. Okay? Any questions there? All right, good. Well, that's about all for today. So this would be, so on Monday you'll have homework